Right. Welcome, guys, to the EIT webinar, OpenFOAM, an open source CFD alternative. Basically, I don't know if you've attended a webinar before, but you should go into My Settings and disable your sound and notification settings, etc. That should be fine. It should be fine. Right. So OpenFOAM, the open source CFD alternative, it's presented by me, as you figured, Dr. Johan van den Berg. So basically, a bit about myself. You will get a certificate of attendance, and you will also receive a copy of the slides on the video recording. The slides aren't that useful, but the video recording is going to be very, and I'm recording right now, so it's all fine. Right. So about EIT, as you know, we are an engineering institute for technology. So we provide training, and we provide certificates, we provide degrees, master's degrees, bachelor's degrees, everything. So if you have a problem with engineering, you can come to EIT and we'll sort you out. So yeah. Right. Is my volume okay? Can you all hear me? Is it fine? Or do I need to up my volume? Or do I need to do something else? Okay, I'm assuming it's fine. Okay, so yeah, a bit about me. I am Dr. Van Berg, as I stated. I obtained my doctorate from the University of Victoria in the late 2021 in experimental flow boiling. I started working as a lecturer for EIT in November 2021, so 2 years ago, and I accepted a postdoctoral fellow position in November 2022 in Poland, studying nuclear boiling, computational nuclear boiling. Because I figured, well, I've done experimental flow boiling, so I might as well focus on numerical. Numericals should be easy, right? Simple. Yeah, not quite. So yeah. Yeah, Samuel, you keep raising your hand. Is there any question you want to ask, or is there anything you need, or can I continue? Okay, so I'm not receiving anything. So yeah, I will deactivate my video. Samuel, what's up? You are raising your hand. Is it a question, or do you want to ask a question in chat, or do you want to talk to us? What? Okay, I'm assuming it's a mistake. Right. So I accepted my postdoc in Poland, and that is what I'm doing at the moment. And that is why I want to tell you all about OpenFOAM, the wonderful world of OpenFOAM. Yeah. Right. So without further ado, let us do a quick overview of what is going to happen today. First, a welcome introduction, detailing the goal of today's webinar. Then I will be going over what OpenFOAM is very briefly, because I can spend hours and hours talking about OpenFOAM. It's too much. It's literally too much. But what OpenFOAM is, where to find it on the web, how to install it. Next, I will go over an example case, going over the basic structure of an OpenFOAM case, running it live. And as soon as that is done, I will show some of the possibilities of OpenFOAM, the open source post-processing, and share some words of caution and wisdom, I hope. Finally, I will go over a plethora of solvers and tutorial cases available, as well as pointing out some very, very good online OpenFOAM sources. I highly recommend after this talk, if your interest has at all been piqued, you should definitely check out the resources I'll be pointing out. Right. Finally, it's conclusion and Q&A time. So yeah, let's get started. So in modern engineering, CFD, computational fluid dynamics, has become so ubiquitous that it's almost accepted that an engineer will be comfortable applying at least some kind of CFD software and using it to inform the designs. All right. So major multi-million-dollar companies have entire teams dedicated to implementing CFD solvers in a GUI form and supporting software. ANSYS, COMSOL, Dassault, SolidWorks, they all come to mind. Like, right. Can you hear me? Is the volume okay? Because I keep getting your hands raised, and I think you can't hear me. Philippe, can you just say yes in the chat, or give a thumbs up or something like that? Not raise your hand. Right. Okay. I'm assuming you can hear me. Yeah. Okay. Well, the volume sounds okay on my side. It looks okay on my side. So, oh, carry on. Yeah. Well, unfortunately, the support that you get from Dassault, ANSYS, COMSOL, whatever, and the ease of use, they come with a major price tag, which is no problem if you are part of a large business yourself, engineer. But what is a small engineering company supposed to do? Or what if you are working on a field, a specialized area, which the major companies haven't implemented yet in their codes? What do? Well, OpenFOAM to the rescue. Today, I want to run over a complete install of OpenFOAM and just give you an indication of the vastness of OpenFOAM. It's amazing. It's amazing. I mean, in December I was a complete OpenFOAM noob, and now I'm less of an OpenFOAM noob, and I'm converting. I'm proselytizing. So yeah, right. So do note that I will be leaning heavily on my own laptop terminal and the OpenFOAM site, flitting between those and this presentation regularly. So yeah, okay. So I've been throwing the term OpenFOAM around willy-nilly, assuming that you even know what it means. But for completeness sake, let's take a step back and give a very brief history of OpenFOAM. OpenFOAM stands for open source field operation and manipulation, right? It's a mouthful, but like OpenFOAM, that's much easier, right? The first release was in 2004, but it has a long history before that. I think the initial OpenFOAM idea got made in 1992 at Imperial College London, but it's gained so much traction in industry and academia lately that from 2016 it has had a bi-yearly release every year in June and December. So it's got a release of a version and bug fixes. It's amazing. It's amazing. So preceding the first release, it had a long development history, as I said, and there have been some hiccups in circa 2010 arising from some of the licensing disputes. I won't bore you with the details. You're welcome to look it up if you want to. But suffice to say, it's an open source, very quick solver, written in C++, modular, runtime flexibility, and I hope to at least show you what it means to be a foamer, okay, to use OpenFOAM. It's amazing. Right. The beauty of it is that you don't need to ever touch C++ to gain use out of OpenFOAM, but you can implement your own solver in OpenFOAM, right? Which that fact has only allowed the solver to grow and grow as academia and industry implement their own solvers, and it gets included in OpenFOAM in the main trunk of OpenFOAM. So yeah, right. Okay, as I said, I want to give you a complete overview of OpenFOAM, including explanation. So I will be switching windows now. Don't worry, I'll be talking you all the way through it. So yeah, let me share my screen, entire screen, built-in display, share. Right. I'm assuming you can see it now. I hope so. Yes, you can. Right. So If you open a browser and you type in OpenFOAM into Google or DuckDuckGo or Yahoo, whatever search engine you use, you will find the openfoam.com website immediately pops up. So yeah, clicking there, it takes us to the main site, from which the two main areas of interest to us personally is the documentation and the download section. Right. So I'll get back to the documentation in just a minute, but if you hover over download, you'll see options for the three major operating systems. So Linux, Mac OS, and Windows. So you pick the appropriate one and you follow the detailed instructions online. So let's say I want to install in Linux. I click on Linux and it will take me to a very, very detailed page. And you've got options. You can either download a precompiled version or you can compile it from source, etc. It depends. It's all dependent on your need, right? So because I've got a compiled from source version on my laptop already, skip the step. But just a word of caution. I don't know if you've ever been exposed to Linux or Ubuntu or if you come through a terminal, because that is the way OpenFOAM works. The OpenFOAM works with the terminal, and I don't like using Windows for any coding related work. Linux and Mac OS are much more stable. Word to the wise, switch to Linux, explore OpenFOAM. You'll thank me in future. You'll thank me in 2 years from now. It's amazing. Linux is amazing. Right. Before we explore my installation on my computer, let's loop back a bit to the documentation. So in here, you will find a user manual, overview, an online wiki, a coding guide, etc. It's very, very useful stuff that I highly recommend you read in your own time. But let's click on the tutorial wiki, well, the tutorial guide. So user guide to tutorial wiki. Yeah, so basically, this details the tutorials. Okay, so we offer a collection of tutorials. Let's click on that. No, what am I doing? Where is it? Documentation, overview, code wiki, user guide. Huh, it's gone apparently. Anyway, so let me just Google it. Dam break tutorial. OpenFOAM. Okay, where is it now? It disappeared. That is very, very strange. Okay, so whatever. Okay. Overview. Here it is. So yeah, sorry, you click on overview and then you can click on the tutorial. So yeah. So basically you've got a PDF version and you've got an online version, but usually I use the online version because the online version is much more up to date. Right, cool. So we click on the tutorial guide and you'll see there are a few tutorials that are highly detailed. Incompressible flow, multi-phase flow, and even a stress analysis problem. So I've decided to go over the multi-phase problem because the results are fairly exciting. It's a wave breaking over an object, which is pretty cool, and it solves fairly quickly. So we can run it immediately, and we can see the results. And it allows me to point out various things particular to an OpenFOAM case. So basically, like if we click on multi-phase flow, breaking up a dam in the tutorial guide, we will be solving this. A water column in a 0.5 meter box, and the water column gets released, and the water column sloshes over the object. Right, so it looks pretty cool, and it allows me to like show off OpenFOAM. It's pretty cool. Right. So now that you have OpenFOAM installed on your PC, I'm assuming like let us say where we installed it. you should have the tutorial folder ready for action. So let us quickly go to the tutorial folder in OpenFOAM. So home, OpenFOAM, run tutorials. So as you can see, the tutorials on the website, this is much more than the tutorials on the website. We can combustion, compressible flow, discrete methods, direct numerical simulations, financial flows, finite area flows, heat transfer, incompressible flows. Oh, it's amazing. And the thing is, they detail very little on the internet, because these are basically the introduction cases, right? So let us check where it is. It's in multiphase, interfoam, laminar, dam break, right? So let's go there. So multiphase, interfoam, laminar, dam break, right? So let us look at the case. It's pretty clean and concise, right? So it's got a system folder, it's got a constant folder, and a zero dot orig folder, an all clean script, and an all run script, right? A detailed description of what each folder contains is available in the user guide. So if you go here and you go over to the overview and you access the user guide, you can read exactly what each folder contains and what each case contains, right? But for now, I just want to go over it for this case, for this specific case, right? So a detail, for our purposes, the system folder contains everything to do with the system solver. Okay, so don't worry too much about it right now, but for our purposes, we can say it contains the mesh and the control of the solver, right? Okay, the constant folder contains what do you know? The constants of the solution. So let me open it. So it contains gravity at 9.81 in the y direction. It contains let me just open it contains the transfer properties, so for water and air, because we are simulating a water column in air. And it contains the viscosity, the rho, the density for water, and it contains the nu for air and the rho for air and the surface tension, because that is all that we need for the solution, right? The ORIG folder is very important because it contains both your boundary conditions and your initial conditions. So let's look at the U velocity. So your left wall is no slip. So let's go to the case. So the left wall is no slip. The right wall, the right wall is no slip as well. The lower wall, the bottom, is no slip. The atmospheric is pressure inlet outlet, and the default phase is empty. So front and back is empty. That is just a nuance of OpenFOAM. It's traditionally three-dimensional, but it uses two-dimensional cases by using the empty condition for front and back. So if you look at this is two-dimensional, and the front and the back are called empty. So that is just to force it to think in the two-dimensional node, right? So the ORIG folder, when you're running, it creates a zero folder, and as you run, it creates a time folder. So in other words, like let's say you want to run for 10 seconds and you want to output every second. So like in system, you go to control dict and you want to run from start time 0 to end time 10, and you want to output every 0.05 seconds. So the first output will be 0, the next output will be 0.05, the next output will be 0.1, the next output will be 0.15, etc., 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 until you use 10. But you'll see. Right. Okay, I've got a question. Someone's hands up. Why? Okay. Okay, so I'm assuming you're fine. Right, cool. Right. So let us go to the scripts. The scripts are basically the all clean. It's basically just to clean the case, so it's not important for us right now. And the all run, which is very important. So just keep this in mind. I'm going to come back to this later. But if you run a case, if you run any tutorial case, it will contain an all run script, which will tell you exactly what the case does. Right. Right. So the restore 0 directory basically copies the ORIG folder into a 0 folder. So let us do that manually for now. Okay, so copy, paste, rename 0. Right. The second thing we need to do is we need to run block mesh. Block mesh. That is the inbuilt tool that OpenFOAM uses to create a block mesh. So a block mesh is basically a structured square mesh. So let's run it. Block mesh. And it completed successfully, and it gives us results. Right. So let's do we do next. All right. So let us take a look at the block mesh first. So we use ParaFoam. ParaFoam is basically a specialization of the ParaView open source third-party visualization tool. So yeah. Okay, I'm running it right now. It's supposed to start up. Right. Okay, where is it? Okay, cool. So we apply, and this is our block and the obstacle. But where is the water? Where's the water? Well, we haven't really told OpenFOAM there is water. Where's the water? Well, we haven't told OpenFOAM where the water is. So next thing you do is we need to let me just quit OpenFOAM. ParaFoam. The next thing you do is run set fields. Set fields. And that depends on, in the system folder, the set fields dict, you basically say, well, I've got a box in the lower left-hand corner of my overall box, and I want to set the alpha of the water to be 1. So just to take a step back, the alpha of the water, it's basically the way OpenFOAM uses in this solver to specify whether there's water or air. So 1 is water, 0 is air. That's basically it. So if you are interested in reading it, you could go into the user guide and you could read what it solves to get the alpha. It basically solves the volume of fluid equation, in which alpha is either 0 or 1. So yeah, and I'm not going to get into it right now because it gets complicated. It gets complicated. But I'll show you why it gets complicated later. Right. So set fields. Right. So we set the field. Let's check it again. ParaFoam. As soon as it starts running. Okay. Right. Apply. Don't skip 0 time, please. And now, hey, there's water. Amazing. Time step 0. We've got water. We are ready to start. So if you look at the all run file, it'll say run application, get application. What the get application does is it goes into the control dict and it runs the application you specify. Interfoam. So let us do that manually for now. Okay. Interfoam. And as you can see, it's running like a boss. So it's running blisteringly quickly, as you can see. So let's just scroll up, and it usually outputs this to a log, but you can keep track of the solution, and you can sort of gauge whether the solution is convergent or divergent, etc. So in other words, it's converging at the moment because our iterations are very low and our residuals are very low as well. But you've got control over this. But I'm not going to get into it right now. But just know that if you want to use a different kind of solver, so if you want to use, instead of a Gauss-Seidel solver, you want to use a Jacobi solver, you could implement that in OpenFOAM, and OpenFOAM has it. And you could say, well, I don't like this, so let us rather go into the system and change the solution. Yeah, so I'm not comfortable with the symmetric Gauss-Seidel. I'd rather have a Gauss-Seidel or a Jacobi or a PCG, whatever, right? But as you can see, it's solving pretty quickly and it's almost done. Well, it should be done. It should be done already. I've talked enough. It's done. Done. As you can see, let's look at the results in ParaFOAM. Okay, right, apply. And if you look at the alpha.water, hey, the water is there, and oh, that's up. So as you can see, oh, the water is hitting block, and it's cresting, and it's doing stuff. Very impressive stuff. Very cool, right? Very, very cool. And it'll run for 10 seconds because we said, okay, well, run for 10 seconds. And now you can see sort of part of the problem with volume of fluid. Because if you look at the 0th time step, it's very sharp, very sharp. This is water, alpha 1, this is air, alpha 0, but it's very sharp. But the moment you advance one time step, you see what happens. These cells are 0, these cells are 1, and these cells are 0.5, 0.4, who knows. So the problem with VOF is it's very diffuse. But there are ways of getting a sharp interface. I'm not going to go into that right now, but look at this. It's so pretty. It's so pretty. Right. Okay, so what if we wanted to do like a different down ignitions? Well, we can do that. Like, let's say all clean, okay, and let us adjust down ignitions. So dam brake, ridge. Let's go for the alpha PRGH. Oh, not PRGH. No. Let us rather adjust the substance we're testing. Constant transport properties. So we don't want water. We want water in glycerine. So let's make this 4,000. And well, no, I've got a better idea. What if we are testing in a low gravity environment? So let's make it minus 0.1 instead of minus 9. Right. So I'm not going to go over the manual run again. I'm rather going to say all run, and you'll see it creates log files in the folder you're running. So it's created, and it's created the, oh yes. So as you can see, this is one of the problems in OpenFOAM, is if you specify too many time steps and you specify your write out time too often, you very, very rapidly fill up your hard drive. And that might not seem like a big deal, but trust me, it's a big deal, especially when you are solving nuclear boiling and you want to simulate a second, and you outputting every every 0.5 milliseconds. So yeah. All right. So as you can see, it does the logs. So in other words, when you see run application, where we did it manually, it showed the log in the terminal. Now it pipes the log to a log file for later perusal and for later debugging. So yeah, let's to foam, and as you can see, it is exactly the same as we saw in the terminal. Right. So let us look at it. It's supposed to solve 10 seconds. It solves very quickly because it's a very, very simple problem. But let's check with the gravity. Okay, the gravity is supposed to be less now. Let's look at the U. Yeah, like immediately, the water is all gone. So yeah, let us not skip a zero time. Apply, and as you can see, the water is all gone immediately. So maybe that was a bad idea. But yeah, it's very cool. It's very cool. Oh yeah, that's all right. Thank you. So as you can see, because gravity is less, the impact of the wave is less, and it flows a lot more lazily. Gravity, amazing, right? I could play for hours like this. It's insane. Okay. So yeah, like I said, the log files are available for debugging, for convergence monitoring, for fault finding, whatever. And the thing is, you can restart the case at your latest time. So let's say you want to run for 20 seconds and it diverges at 12.5 seconds. You can restart the case at 12.5 seconds. It's amazing, right? Okay, so that was fun, right? But let's take a look at the folder. Yeah, like as you can see, we output every 0.05 seconds for 10 seconds. This isn't such a huge deal in this case, but like I said, your hard drive can fill up very quickly, especially when you output an ASCII. So if you output an ASCII, you can access the water, and you can see exactly what the water is. It's recommended that you output in binary, usually when you run real cases, but binary it's not human readable. So yeah, right. So if you look at the top on the web, let's look back to the web, it goes into a lot more detail about what we just did. We ran block mesh, and this is the block mesh. This is the block mesh dictionary. And we ran bounding conditions, and we ran the initial field, and we ran the solver. And it goes into more detail on which solver using, and what the values of the solver, what the values of the simulation is, what the solver properties are, which solver are using a Gauss-Seidel, or using a Jacobi, or using a big G stab. It doesn't matter in this case, but trust me, it matters when you are working on the bleeding edge and things diverge. Yeah, that's very useful. Right. So, how do you decide which solver? How exactly do you go over a tutorial case? Well, it's dead simple. Let's say we want to go over the intermixing foam, the laminar intermixing foam. So no, damn break. Damn it, tutorials. So let us say we want to go over the compressible foam. And no, yeah. So I want to go over the acoustic foam and oblique edge it, and open the all run, and if you go over the all run case and you run them one by one until you find out what exactly the tutorial does and what it's trying to tell you, what it's trying to do. Because as you can see, the number of tutorials are vast, like 25 items, 12 items, and that is only subfolders. So as you can see, the number of tutorials are over 100. and it's impossible for all the tutorials to be documented on the web. Right. So you go over the all-run file and you run each line individually, seeing what each does. This may sound pretty basic, but it is a lifesaver. It is a lifesaver. And how do you decide which solver you should use? All right, you go to the user guide and scroll through to the handy dandy code wiki. Overview. And you scroll to available solvers. Damn it, sorry. Online user guide, and this will show you the available solvers that you can use. So in other words, like let's say you are interested in compressible flow with turbulence. You go over you go over the available solvers, and it should tell you, okay, well, this solver is made for this case. This solver is made for that specific case, and you find the closest solver to what you want to model, and you adapt it for yourself. Right. Right. So let us go back to the slides. I think that is cool. And share. Second while. Okay. Share now. Right. So I hope this was useful in whetting your appetite for OpenFOAM. Let's go. Okay. Yeah. So a word of caution: just because it looks pretty, it's a colorful diagram, does not mean it's true. So, taking the dam break case, for example, you should go over mesh independence, and you should validate your case against either experimental values or analytical values. That is like something that I can't stress enough, because unfortunately, CFD also stands for colorful diagrams, and that could be all it means. So yeah, right. So this was literally just scratching the surface of OpenFOAM. How far down the rabbit hole do you want to go? Do you want to make a mesh analysis and space claim and import into OpenFOAM? Yeah, you can do that. You want to add a custom source term to velocity? Well, you can do that. You want to output the velocity at a certain point in space, but only at a certain time, and only if the y velocity is higher than a certain value. You can do that. You can do that. It just takes some reading, practicing, and yes, you will fail at times, but that is the learning process of OpenFOAM. It's so powerful. It's quite beautiful, right? There is so much left to say. I haven't even gotten to solver stability, priming the system for quick solutions. So much to say, so little time. So I'm going to sum up right now and get to questions. OpenFOAM is extremely powerful, and the information on its use is continually growing. Any problem you can encounter probably has been solved before. So you can go to CFD online and browse the forum, because it's probably a phenomenon or you can ask for advice, and you will probably help, because the CFD online community is very helpful, very decent. If you want some additional, far superior in terms of presentation videos, you can check out Tobias Holtzman or Joseph Nagy or Theo Ong on YouTube. Theo Ong is especially useful because he basically takes all the tutorial cases and he runs them and talks you through the pitfalls. Maybe I'll show you. I will share my browser right now, and I'll show you that. Finally, and this is very important, the API guide available on OpenFOAM is priceless. Even though it's a bit obtuse at times, I'll show you now. But it's sometimes the only way of figuring out the code and seeing it applied, and it's like, oh, that is what it means. that is what the code is doing, right? So I'd also want to show you like the motorcycle that I lured you with to get to this share to get you to attend this. Basically, the motorcycle is an illustration of OpenFOAM's basically meshing abilities. So let me show you. It's in, I think it's in. Okay, scroll. The tutorials. I think it's in incompressible, simple foam. Ooh, simple foam. Simple foam. It would help if I could aim simple foam, right? Motorcycle, motorbike. Okay, I'm just gonna open in terminal. So I have not run this case because this case takes about 40 minutes to solve, but I just want to show you. Oh yeah, I need to tell Linux that we're looking at OpenFOAM. I just want to show you the motorbike model that it's possible to get in OpenFOAM. So let's apply, and I just want to look at the motorcycle group. So as you can see, this is a pretty cool motorcycle. And the way the simulation works, it's got a steady state solution. The motorbike is driving at 120 kilometers an hour down the highway, and it's basically you can look at the velocity, or you can look at the pressure, or you can look at the turbulence flow. It's pretty cool. It's pretty cool. Right. So now I just want to show you the Tobias Holtzman or Joseph Nagy. Chrome. Okay. YouTube. Go on. He is very, very useful, and I highly recommend giving him a watch. Or Joseph Nagy. He is a master of OpenFOAM. Nagy, right. Block. But if you really want to be amused by OpenFOAM, he is boss. He is so amusing, and he's so witty, and he's so useful. I learned a lot. Right. So I think that is pretty much all I have to say, and that leaves us with 15 minutes for questions. And I want you to ask me questions, and like just hit me, like because I love OpenFOAM. It's opened my eyes to a whole world of CFD. It's amazing. So yeah, thank you for listening to my ramble, and I hope it was useful. I hope at least some of you will install OpenFOAM and we'll play around with it. I mean, you don't have to master OpenFOAM, but it's useful for you to just know of it and know there's an option. Accept answers, accept Dassault, accept accept console, right? So any questions? I'll just go through the upcoming courses. So just for you guys, just check this out. Right. So any questions? Any comments? Anything I can do? Anything I can show you? I can't really solve anything in 15 minutes, but who knows? Anything can happen. Right. if you want to ask a question, okay, Prosper, you can speak to me, or you can type a question in the chat box. Okay, cool. Floor's open. What's up, guys? No questions. No questions at all. So either you have been converted to OpenFOAM, or you think I am talking the biggest load of fairy dust ever. Prosper, what's up? I've seen you raise your hand. Prosper, Samuel, Nonofo. If you've got questions, like you can ask me, either personally via chat, or you can type it out, or okay, Samuel, Nonofo, Zimasa, Prosper, hit me your questions. Otherwise, I'm going to assume that I blew you away, and you will be downloading OpenFOAM immediately, and tomorrow you'll be OpenFOAM masters. Okay, I'm assuming like you don't have questions. But yeah, so if you've got questions, and you don't, if you can think of a question and you want to ask me later, you can email. I think you can email EIT and they will forward the email to me. But yeah, Chigueda, yeah, I keep seeing raised hands, but I don't see questions. I don't see questions. Okay. Okay. I guess. Zimasa. Okay, cool. Yeah, so just to give you a taste of OpenFOAM's abilities, you can also have multiple fluids mixing. So just to give an idea, I'm going to share my screen again, unless you've got other questions. But I just want to show you this. Okay, cool. Share screen, entire screen. Oop. Share, right. So I just want to show you the other multi-phase cases, because like you saw, the multi-phase interfoam, it contained only laminar, it contained dam break, it contained capillary rise, it contained sloshing, it contained VOF Lagrangian. So I think, let's check it out, not waves, so it's got compressible multi-phase interfoam, yeah. So if you look at this, dam break four phase. So if you go into the system or the original folder, you got alpha air, alpha mercury, alpha oil, alpha water, and you got P air, P water, P mercury, P whatever, and you've got PRGH for water, air, whatever. So this is an example of OpenFOAM, the power of OpenFOAM. Or if you want to go into modeling a solid, you could also go into heat transfer. That is what I'm doing at the moment. Heat transfer, CHD multi-region foam, and snappy multi-region heater. Over here, you'll see the bottom air, the heater, the right solid, the left solid, the top air. You can go crazy. You can go crazy with OpenFOAM. It's amazing. Right. Okay. I think that is just about it for this webinar. We've got 10 minutes remaining. So if you've got any questions, please hit me. I can answer anything. Well, I can try. I can try. Yeah, sure. Right. Okay. Olusegun, yeah, I'm assuming you don't have any questions. So that will mean I'm stopping the recording. Let me just share the file. Why will it share? Share now. Okay. Okay. Yeah. So I'm going to stop the recording now. And yeah, it's been fun, guys. It's been real. And I really, really, really hope that some of you at least have got a taste for OpenFOAM. I know this was a very, very quick, very rough, very it wasn't much of an intro, but I really wanted to share it with you guys. Right. So I'm stopping the recording. Thank you guys. I will see you in the next webinar sometime. Yeah. Goodbye.